Welcome to another Draft Physics presentation. Sort of a response video to Looking Glass Universe. Call her Juliet, let's say. Yeah, the Juliet of physics. Anyway, so this video is what is spin. I've watched a couple of others on different interpretations of quantum mechanics, and you know, she doesn't seem convinced about anything, but thinks there's something like an answer in some of this stuff, apparently. So she's not really a dissident, but she's not one of the sheep either. But, you know, so I don't know if that's good or bad. That's like having it's like somebody being a fence sitter. They're always suspect, and so maybe just shoot them first. You know, the neutral people are just as much trouble as the enemy most of the time. But anyway, we'll give her the benefit of the doubt on some of that. So the question is, what is spin? And she doesn't really have a great answer. And on top of that, in my opinion, the real questions to be asked are the more basic questions, like what is inertia? What is velocity? What is acceleration? What exactly is momentum a byproduct of? So again, a real problem with a lot of this conversation is they use the word, she particularly, particle, okay, because they want to turn this into a particle physics, and they want to turn it into this idea of a quantum particle, this idea that everything is a quantum thing, that everything has a, well, I'm not going to put words in her mouth, but an anti-thing, or everything has an entangled thing, or everything is a thing is the same, and the things aren't anything like each other in a sense. That a photon thing is quite different than an electron thing and an atom thing. They're not the same thing at all. They can be made of each other, but they're not the same. The flour is not the cake, kind of thing. So we'll play some of this, and I guess then I'll do some of my commentary and draw somewhere in between there and see how it goes. So we begin.
But what is it? In this video, I'll explain how we know spin exists, but also why we don't understand it.
Right, so is the particle spinning, it said, and the answer was no. And why is it called spin? Well, because they call lots of things things that have nothing to do with what it actually is.
Spin was a latecomer to the quantum mechanics party. Even after...
Oh, we probably need more volume. Sorry about that. Perk it up a bit. So, spin was a latecomer to the quantum mechanics party, she said. And it's not even a... You know, it really didn't show up because it really doesn't have a good definition.
Schrödinger wrote his famous equation and everything seemed to be working. People didn't realize it existed. Then people realized that some particles seemed to have odd magnetic properties.
Right, so this is Schrödinger wave equation as they call it, but it's really just a pattern equation. It really, when you decipher through all this funny gibberish, there's a sine theta in there somewhere that's really deciding angles of where things go. But all of this is the approximations of permutations, blah, 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 or something. I don't know what the little forky thing represents. I don't even really realize, you know, there's an equal sign in this equation, and so it seems like this line forky arrow thing on both sides, you could just get rid of the line forky arrow thing and just have the H bar thing. This is the H bar, I guess. This is H hat. Yeah, so H hat equals I H bar D T D thingy, however they say that divided by thing. But anyway, yes, whatever. Wonderful equation. I love it to pieces. So much fun.
Properties the original quantum mechanics didn't predict.
Spin what? I missed that. Whatever. But how do we explain that question mark?
And the source of that was labeled spin. To understand this, we're going to need one piece of...
So it's all about one experiment, this detecting of spin by a process of changing a magnetic field, switching it up, down, up, down, up, down really fast, reversing it, and throwing things through it and see what they do based on whether or not they have any polarity. If they have no polarity, it won't bother them, but if they have any polarity at all, they'll start to process. So they'll start to go forward and rotate. And the problem is, though, is that theoretically, based on how much angular momentum, they should land in various positions, but they always go all the way up or all the way down, all the way left or all the way right, something like that.
Classical electromagnetism theory.
Right, so now they're going to say things. This is where the assumptions are, in my opinion, the mistake. Is the premises going into their argument about what anything is are always flawed axioms of reality.
Whenever a charged particle moves, it creates a magnetic field.
Right, now that's sort of not a law, that's sort of a tendency. Okay, so but yes, the idea is that energy leaves that little thing that's moving this way, and that energy leaves perpendicularly. So that's always something to understand. The magnetic field doesn't just go everywhere. The magnetic field is created in specific directions to the movement. And let's understand also that charged particles never move on their own. They have to be propelled by a charge differential, a voltage. Whether it's a proton or an electron, it has to be moved by a charge potential. That is magnetism, which is a kind of voltage, or an electrical voltage. So it has to be moved by an imbalance in the field around it to be propelled. It doesn't move on its own. You can't throw it like a rock and it just keeps going like a rock kind of thing. It always loses its momentum, so you have to keep accelerating it to keep moving it. Something that needs to be pointed out over and over and over again.
This is pretty amazing, and you can see it for yourself by putting a compass next to a charge-carrying wire.
Right, but that's not exactly like electrons moving freely, right? So we know the wire and the electrons, we know they're not going anywhere. They're specifically going through the wire, so they're in a charged field that's basically saying stay here next to your protons. And they're moving in a direction, this way, let's say, and they're producing a field this way. So clearly, in my opinion, what they're doing is converting momentum this way into energy this way, because they have to keep being propelled. You have to keep accelerating them, either this way or this way. Now, if you accelerate them this way, the field comes out this way. You accelerate them this way, the field comes out this way. So the field's always perpendicular, whether they're going up or down, and the only thing changing it is the right-hand rule in the sense of what direction the polarity is. So a magnet will switch, a compass needle could measure the direction that the current's flowing in because of its polar change. But clearly that example, free electron being pushed by a voltage, not in a conductor, and electrons in a conductor, isn't exactly a perfect analogy. But anyway, let's play along.
In fact, if you have a charged particle going in a small loop, this not only creates a magnetic field, that field pretty much looks like it's from a bar magnet.
Right, now this is where this huge assumption comes in that somehow, because the electron is creating a change in the field, that it's doing magnetism entirely. Now, if they understood that the electrons and the protons are like the S and N on that magnet, one's a monopole, S monopole, and one's the N monopole, they might understand that it can be creating a field, but it's only an S field or an N field. It's not both fields. So half magnetism is really hard to tell the difference between something that's half magnetic, and that is creating an imbalance in the N field, from something that's creating an imbalance in both fields. Because magnets will react to any imbalance, whether it's a half imbalance or a full imbalance. That is, if you create more north magnetism or more south magnetism, the magnet will repel and attract as if it was both being produced. But essentially the electron isn't. So there's two things wrong with this story. First, the idea of the electron spinning doesn't make any sense, because where does it get the energy to do that? I mean, going around like this, not spinning like this. So clearly going around like this requires momentum, energy, velocity. And what can we say about electrons from experience in other experiments? That electrons can't be, I can't take one out into space and flick it to the moon and it gets to the moon. It can't hold its velocity. Something about the universe, the space, somehow consumes its momentum. It drags it down and decelerates it. So de-accelerates it. So electrons don't have magical energy where they can just sit somewhere and spin. Doesn't happen. They run out of fuel. They need to be re-accelerated to continue to spin. So obviously any electron that's spinning is spinning because some force is pushing it. So that's where the axioms are broken here. So she has a kind of equal sign between an electron and a magnet. And there really isn't any equal sign there, because it's really just electron equals S pole of the magnet. It doesn't equal magnet. It actually equals the north pole, because that's the energy it will be excreting. But anyway, let's play along.
So then we expect charged particles moving around in circles to act as little magnets. Since that's something we know...
Right, so that's a wrong expectation built on a wrong understanding and the wrong assumptions, in my opinion. So you're starting off with not really hard proven facts. They're mushy facts. And now you're going to build a whole bunch of more crap on the mush.
From classical physics, it was built into quantum mechanics too.
So it's not a classical thing at all. So it's not like Newton didn't make guesses about any of this stuff. So there's nothing purely classical about it. And if I was to take the classic and move it forward without making it wooey quantum mechanical and just make it mechanical, the argument would be is that the electron is the magnetic monopole. One of them.
From the start. But eventually some experiments showed that there must be some other source of magnetism. I'm going to explain one of those, a simplified version of the Stern-Gerlach experiment.
Right, so this Stern-Gerlach thing, right, as she called it, she could have just said it reverses the magnetic polarity. That's all it does. It just reverses it. Yeah. And you'd have certain expectations about what would happen to a charged particle or a neutral particle when you throw it in there. And what they do it with traditionally, I guess, is silver atoms, which are dielectric, are ferromagnetic. No, are what's the word for? Not a permanent. Not they can be magnetized, and so what you're doing is throwing something that can acquire magnetism into a magnetic field, and so it becomes magnetic, and now then it starts to react as a magnet in the field once you put it in the field. So it's never going to be neutral.
Let's say we have a bunch of electrons by themselves. They are charged, but they're not doing little loops, so they shouldn't be magnets.
Right. So this whole idea, again, is based on an understanding that I would argue is incorrect, that the the function of the electron doesn't have to do explicitly with movement. The fact that it excretes force differentially has to do with two factors. Not only the fact that it has to be accelerated, and then it always decelerates, creating the perpendicular energy, and when it's associated with a proton, it's interacting now as a magnet, in the sense the electron and proton are reacting to force mutually, inductively. And as the electron moves towards the proton, it's now creating force perpendicularly in a different direction, a different plane.
We test this out by putting them in a Stern-Gerlach apparatus. I'm not going to explain how the machine works, but what it does is
it's a type of magnet. Now, see, she could have just said a type of magnet that's switched on polarity. It's just switched back and forth, back and forth, back and forth, really fast.
This. If a small magnet is placed inside, it measures its orientation.
All right, so let's just understand that this just now has to do with the fact that once you create a magnetic field, the magnets will react like a compass needle. They'll turn to orient to the field changes. And so as you do that to something magnetic and you're switching the polarity up and down, you're going to cause it to move down, and then it's going to have to move back up, and it's going to be doing that while moving forward, and that ends up being kind of you'll end up creating a kind of screw motion, procession, where it will acquire, and that'll spread ultimately. And depending on how much the argument is that it's going to turn, how much it's turning or spinning would have to do with how much of a tilt it had to start with, and that could be randomized. So you could argue that so this device is going to end up with a 50-50. Half the neutral things will end up going one direction, half go the other direction, and that happens with electrons, even though they're not neutral. But for the sake of this argument, they're neutral in the sense that you're just really measuring what part of that turn they're in when they go to a target. They're either going up or they're going down when they finally get to the last, when they get free of the machine. They're either in the process of going this way or they're in the process of going this way. And in that sense, they're 50-50. But you could argue that happened when they went into the machine, because the initial movement was, the orientation of the machine is, say, positive, negative, top positive, bottom negative. So the magnet, the electron, is magnetized in a direction, so to speak, if it was neutral, even though it's not. And so the tendency is going to be to move up or to move down, depending on what that first state is. So when it first went into the machine, its fate was decided in terms of it was inevitably going to come out of the machine in a certain direction. So it's all deterministic. You put it in, its orientation is going to be decided by what the cycle of the machine is at that exact second. You've already decided left hand, right hand, glove, and your results are consistent with that. Alright, so now I'll do the drawing half of this to explain some of this in draft physics speak. The alternative explanation. So again, the important feature is that photons, which are, let's call them force bits, so there's these force bits, and the photons would just be bits at a separation, moving the speed of light. So they're traveling c, and they're just made of little discrete blobs at a specific distance from each other, and they call this frequency, or they call this wavelength, or they call this period. And it's all the same thing. It's just a distance or timing cycle between them. Because they're moving the same speed always. It really just doesn't matter. I wish this was a little better focus. It's just so, I mean, it's a little brighter now, but it's, damn. It's just a little, it's just not bright enough. There really is enough light. So if I zoom in, it gets kind of fuzzy, I think. I mean, if I go closer, but it's I'm going to have to because it's just not quite enough contrast. I can't increase the contrast on the lousy camera because it's Linux. But anyway, all right, so, and I would argue that all the things moving the speed of light, that is, all these things we call forces, like magnetism and not electricity, but gravity, are made of these same little bits, and they're causing things to move. And again, the argument is the bits come in two forms, electron bits and proton bits. And the only bits you see as light are these black ones. These are the electron bits. And so electrons are only moved by the electromagnetic spectrum. The electromagnetic spectrum is electron sensitive force. And so there is no known spectrum of proton force. But anyway, just to make this understood, that these things, okay, so you have these force bits, like the photons, moving at constant speed. Then you have the two types of atom bits, which are the electron and the proton. These are the important ones. Okay, so you have two kinds of little force bits and two kinds of matter bits. And the neutron is just a combination of these two. It's just a bastardization of the two. Yeah, I just wish that was... it's just irritating. It looked a little better before. I like that I can just do this in pencil, which is, makes it easier. But just, really is enough light. Let's see, if I tilt it that way, it's a little better. Yeah, well, I'll work on it in my spare time. Looks good on the paper, in theory. Yeah, just if you just had some camera adjustments, I could, this would really be a good way to do this, because this is a lot better than the old way. But I guess I have to come up with some different, more intense lighting source. Okay, just move the light around and see if I can do that. I don't think it'll work, but it's too much, too little, not enough, not bright enough. Yeah, it's just still doesn't quite do it. Alright, so that's a waste of time. It'll have to be called a waste of time. Alright, well anyway. Sorry, wasting your time. Alright, so these are the matter bits. These are matter bits. These are force bits. These go the speed of light. These, again, can only be accelerated while you constantly hit them with a force. So a force has to hit them in some sort of uneven manner for them to move. There has to be more little bits hitting from this direction than from this direction for them to move. They have to constantly be accelerated to move. Alright, so one of the features that I have attempted to describe, but it gets a little tiny bit complicated, is that these matter bits do two things. When the black energy hits an electron, that is, the electron energy hits an electron, the black force bit, it just reflects, and the electron acquires momentum in that direction, and it excretes, when it decelerates, that force. So it's essentially grabbing, holding an extra bit going this way, and it will excrete when it slows down. Okay, the field is, there's an argument here that the field energy keeps hitting it and that it will wear it down, slow it down. So anyway, but the point will be is that when it decelerates, it will essentially readmit that energy in one of the perpendicular dimensions, in, out, left, right. And that's what's expressed as the EMF, the magnetic field changes, the magnetism. Now the trick is when it's accelerating, it will essentially exchange for this little forward momentum. It will essentially excrete red potential, the proton force, and when it slows down, it will emit electron force. So it essentially is going to exchange. To make this black arrow go forward, it's essentially going to release. So you could almost argue it has to always stay neutral, in a sense, in the inside. So if it accepts more energy in one direction, it has to release energy in another direction. So when it's accelerating, it will release red arrows perpendicularly. When it's decelerating, it releases black arrows perpendicularly. And it's the absorption. So the idea is that if when it's moving, it's essentially absorbing force going this way. This arrow ends up inside. This thing moves. And so the field it's creating forward is minus this little black arrow. This little black arrow doesn't get here at the speed of light. It gets stuck in here. So it's not going here. It's not going to hit here. And that means the other object feels that force change in the sense it has more energy hitting it from one direction than the other direction, and it moves towards it by doing the same process of exchanging this direction for a release of energy in the perpendicular direction. All right, now that's a little bit, it's a little complicated, but not too complicated. So you just understand that there's two possible ways that force interacts. If it's red force on red force, it just reflects. If it's black force on red force, it leaves perpendicularly. So those are the two fundamental rules. So, and the same is true for electrons. The black things. The electrons do exactly the same thing, they just do it opposite. That is, if black force hits, it reflects, and if red force hits, it goes through and leaves in one of the perpendicular directions. All right, so so that explains why movement of electrons or protons will excrete magnetism, a field of energy, a change in the field. So you have to understand there's around everything, these little arrows are constantly hitting. This force, like the cosmic background radiation, is everywhere. So you could argue, if I take a free electron and I just have it in this free space, I just wish this lighting was a little bit better. I mean, it doesn't have to be much better, just a little bit better. So maybe we'll go back to the big crayons for this. Big crayons. Because it just isn't quite good enough. All right, so if there's a free electron in empty space, you can kind of understand that what goes in goes back out. So all around it, the same amount of energy would be leaving as is going in. These are just pure reflections. And you can sort of understand that the movement of the electron would be, yes, it would go jiggling around, but it wouldn't go anywhere. For every bit of momentum it gained in one direction, it would gain momentum in the opposite direction. So it would be a completely even exchange. Now, when you do that, calculating the effects of the red force on an electron, it's really the same thing. It's just that you have this, the fact that the reflection doesn't go back. So stuff hits come in one way, it leaves perpendicularly. But if you rotate that in 360 degrees all the way around, you sort of understand that it's the same amount of energy going out in the end that came in. So there's always a perfect balance of that total amount of energy. It's just that the reflection is coming out in a different angle. Oh, jeez, I'm not even in the camera. Okay. So again, the red energy on an electron, proton force, hits an electron, it leaves perpendicularly. So it's leaving perpendicularly in all these different directions. So it ends up looking exactly the same. As much stuff comes in as goes out, constantly. So it's all even. And that only changes when these two objects end up being in proximity to each other. So when the electron is in proximity to, well, this isn't a proton, so we'll just redraw it. Good idea. All right, So when they're not isolated from other influences, that is, when they're associated with each other, what's going to happen is a certain amount of force, that's going to be the black energy, is going to go in the direction of the electron. It's going to come at perpendicularly, and then it's going to go back into it's going to reflect off the electron. So the electron force will get perpendicularly bent by the proton, hit the electron, bounce back, and end up leaving in one of these directions, so perpendicular. So it's going to be leaving in the same plane as the energy that came in. So in a sense, if you just understood that as meaning the energy is going to, a portion of it is essentially going to be reflected. So essentially the energy went in this way, and it's going to now reflect just like as if it was red energy. So just as the red energy reflects, this particular energy coming at this angle, perpendicular to the electron, will in fact reflect instead of doing the 90-degree thing. So clearly on this plane, this plane of the proton, this equator, on that equator there's actually going to be more force. A little bit more red arrows are going to be coming out that way than will be coming up or down or in any other of the planes. So that perpendicular dimension will now have more force than so now it's going to essentially polarize that proton, because that proton is going to create more force in one direction than it will create in the other directions. And clearly the electron will have the same effect. The red force that goes into it will also do the same process of going perpendicular, reflecting off the proton, and ending up leaving as a reflection in the wrong plane. It won't be on it won't balance the 360-degree argument I made before. So if there's a bunch of left turns, you could sort of understand, they're all turning left. No matter, it goes in this way and always turns left. It always turns left. You can understand that if I mess that up and don't do one of those turns and instead do a reflection, that in that plane I'm going to end up with more. Oh, it's out of the picture again. Anyway, I'm going to end up with more on that. There's going to be more energy there and less energy going in one of those other directions because I didn't obey the perpendicular rules, and therefore one of the perpendicular orientations is going to be short energy. So anyway, as I've pointed out before, the reason why a proton and the electron attract is this very reason, that all the black energy, you can't ever create, as with two electrons, anything that gets trapped between them, that is, any black energy that travels between them will just keep bouncing. And obviously the closer you bring them, the more they bounce, which equals more energy. More impacts is more energy. It's like a boxing match or something. It's all about how many times you hit the guy, because each time, let's just say each time the fist hits, it's exactly the same amount of energy, and all you're doing is increasing something of the same amount of energy. You're increasing the occurrence of it by bringing the two electrons closer together. So you're creating more energy by creating pressure. So it's just clearly an obvious reason why electrons repel each other. And the reasons why the electron and the proton attract is because none of that reflective energy can ever exist between them. The red energy leaks out of the perpendiculars on the electron, and the black energy, the electron energy, leaks out on the perpendiculars on the proton. So there can be very low pressure here. So I think that's a good enough diagram to explain why this stuff is sort of always inductive, in the sense that once you create a bias, the bias will be can be exaggerated or complete. once the bias starts, it's like a chain reaction in the sense that that bias will kind of define the spin, the orientation, the momentum, the velocity, however you want to describe it. Alright, so that's probably enough. We'll go back to the video and see if there's anything to add. Clearly you have to watch some of to fully understand what I'm talking about from somebody who has read a completely different Bible. Okay, to understand this Bible, you do have to understand the Genesis story. And so I have a few overview videos in a playlist, and you sort of have to watch a couple of those to get the gist of how all this one force is merely being filtered by these magnetic monopoles. And by filtering it, by them being in an arrangement, you inevitably create force in certain directions because of not only just the movement, but just the orientation of an electron and a proton next to each other will automatically create a bias in the force that leaves on this plane. The electrons will excrete the red force, the protons will excrete the black force. Polarizing, creating a magnet. But you really have to have both of them to create a magnet, a full magnet, complete magnet, and such. Alright, so back to the video and such.
If the magnet's north pole is up, it exerts an upward force on the magnet. If the magnet is the other way around, it exerts a downward force. Of course, there are other orientations. If the magnet is like this, the magnet is still somewhat pointing up, so the force is still up, but...
So I would just argue that this really isn't about a magnet pointing, it's just about a monopole's position and the momentum direction that you're moving it in. The monopoles don't move perfectly straight on their own, just because the field energy will decide how they decelerate. So as you keep accelerating them, they keep decelerating, and they keep decelerating in a direction, a bias. And it can be that bias determines their fate. Once they start going in a direction, they'll probably continue to go in that direction.
Smaller. It's proportional to how much this magnet is pointing in the up direction. Similarly for this magnet pointing down. Say a magnet is on its side, then it has no force at all. But these aren't the only ways the magnet can be oriented either. It could be forward or backward or left or right or any combination. And so what happens there?
Just understand, again, for the sake of this argument, she's claiming an electron is a magnet just because it creates force when you move it. But again, it's not a magnet. It's a monopole.
Well, this machine only measures how much the magnet is up or down. If the magnet is like this, it's still pointing a bit upward. On the other hand, if the magnet was just pointing left or right, or forward or backward, it wouldn't feel any force, and so it would go straight. So what we expect is, if we shot through a bunch of magnets in random orientations, they all land between here and here, and in a pretty smooth distribution. Of course, if we threw in a non-magnet, it wouldn't feel anything and just go through.
Right, so it's really hard to make this point that the idea is there's a total amount of force being applied. So even though they're switching which direction the force comes from, there's a total amount of movement in the electron. And the electron will, as it moves, be essentially reorienting at what plane its EMF is being produced, its counter field, so to speak. And that field is going to react to the field that exists, so it's going to be hostile to it. And so you have to keep understanding that the electron is creating a little EMF at the very time the field is is switching. And every time it switches, it's now got the same field, and so now it repels. So it's doing exactly the opposite of the turn. So in a sense, because of the delay in the creation of that field, and that field's orientation to its reaction to the change in the thing producing the field, that is this machine, the two objects in the machine essentially are a magnet, and it's going to react to the magnet, but it's always delayed. So it's reacting. It always makes a field, and that field is going to end up being the opposite of the field that the orientation of the thing switching all the time. So it's going to be switched to a field that it didn't make. It's not going to be consistent to the one it made. So the little magnet, the electron, is going to be reacting to a field opposite to the one that created the field it's creating. Part of that made sense. Trust me.
So that's what we should expect with electrons. But we do the experiment and find something really odd. The electrons do experience forces as if they're magnets, but they don't spread out smoothly either. Half of them go up to the same height, and the other half go down, again to the same height.
And again, the way I would try to explain that is that once, so the field's created, the electron moves to the field. At the same time as it moves to the field, it's creating a force. Now that force is going to reflect off the other field if the other field changes. So if all of a sudden the energy, say the black force goes up to the top part, that force, and then at that moment that polarity changed to the black end of the magnet, the north, and now it reflects. See, it's absorbed by the mechanism if it's the opposite polarity, but it reflects if it's the same polarity. So the idea is by the time it gets there, the field has changed. That is, the magnet's now an N. It's now going to reflect. It reflects back and pushes it more in that direction. So essentially, it keeps pushing it because the field keeps changing to the opposite, the one that created the force that's heading for it, if you get my drift. So that's why it keeps pushing it in the same direction. Even though it's supposed to be a reversing field, it's always a phase, so to speak, behind.
Let's look at this second mystery first. If electrons really are magnets, we expect them to be randomly oriented, but these results would be like saying that for some reason half of them were pointing exactly up and the other half exactly down. Well, maybe we did something very wrong when we...
Yeah, so again, this can be answered probably a lot of ways, but the most obvious answer is there's always an introduction to the field. So you always have a moment where you're pushing your things into this field. And even though the field's switching back and forth, the initial interaction essentially dictates all the following interactions. So if this is N and this is S, or this is S or this is N, is going to essentially dictate where each electron bias, where it starts, it already acquires a bias. So, and each electron is coming through at a different moment in time, which means they're all going to experience a different polarization, initial polarization. So they're either going to be, from the very initiation into the experiment, they're going to be biased heads or biased tails. I mean, quarters, you could flip a coin. The coins often land in positions that aren't, all the way heads or all the way tails, but they're still forced to go all the way heads or all the way tails.
Prepared them that meant this happened. So to test that, let's do something clever. Let's turn the Stern-Gerlach machine on its side. What that does is, now the machine is measuring how much a magnet is pointing to the left or right instead of up or down. The more the magnet is pointing to the left, the more left it goes. If a magnet isn't pointing either left or right, it just goes through. Now let's use the same source of electrons we had before. We think that they're all pointing up or down, and so they should just go through this machine, and they shouldn't be...
So again, that's just kind of, as I just pointed out, silly, is because they're going to point exactly in the direction that the field is when they meet it. So whatever orientation the machine has, at the second the particle encounters the change in the field, that change is what dictates the orientation of the electron. So you've already, it has nothing to do with what condition your electron was in before it got to the machine. It has to do with what the machine says you're going to be on the first introduction to the force. So it doesn't matter which way you turn it. That's why it would come out this way, is because you're erasing its original configuration. It has no original configuration.
Deflected at all. What happens? Half of them go right and half of them go left. So then they were actually oriented left and right all along, but that can't be right either. Let me explain how to think of this in the framework we built up in the last couple of videos. I can measure the up or downness of a particle, so that is an observable. What are its eigenstates?
Okay, so again, you can't measure any of this. So none of this can be measured without interfering with its up and downness. You can't in any subtle way measure up and downness. You can't measure any of this. You just can't. You can certainly measure a bunch of electrons moving through a conductor, and you can measure the force coming off them, but you can never measure an individual electron. You can only measure the force coming off of it. And your machine doesn't measure the force coming off of an electron. It creates another force that dictates where the electron's going to go. So you're not measuring anything about the electron. You're clearly just interfering with it. I mean, there's no measurement involved. There's just an interference. You're just imposing a force and seeing what it does to the electron, but you're not measuring anything.
Well, this experiment showed that the particle can only be fully up or fully down and nothing in between. So they are the only two eigenstates.
So again, this eigenstate's a fancy word, but it doesn't mean anything. No, the electron has lots of states it's in as it travels through the machine, but again, the total is always going to be the same because there's a certain amount of energy or momentum, and it's going to receive it all in one direction or the other direction once you start it in a direction. So that's just the rule. It will go heads or it will go tails. Yes, that's a rule, but it doesn't land that way, and that doesn't define what it is. So a quarter isn't heads or tails. It can be lots of things in between. But if your device says heads or tails, then that's what it sees. Gravity enforces heads or tails. No gravity, then you don't have to worry about it. You can see it for what it is. But heads or tails doesn't work with gravity, and measuring electrons' preference can't be done by imposing a new force. The new force erases the old condition.
Call them spin up and spin down. Now we can apply the quantum mechanical principle that to fully describe the wave function of this particle, we only need to describe it in one basis. So I can fully write the state of this particle in terms of...
So again, the wave function, there's no waves here. There's angles. It moves up or down at an angle. They were expecting it to move many angles. It doesn't move many angles, it moves one angle in the end. But it does it incrementally through the whole path. So it does move like that. I mean, it does curve its way to the destination, but it's an angle that's moving it. It's not waving its way there.
Up and down. This is weird because in classical physics it wouldn't be enough to tell you the state of the magnet. I can't just tell you how much it's pointing up or down. I need to also tell you how left or right it is and how forward or backward. But
so again, electrons aren't magnets, so you can't orient them with two poles. You can only orient them by their momentum, and that's a voltage behind them, force hitting them from behind. So just understand this real experiment means it has to be done in a vacuum and has to be done pushing of the electrons with a voltage. So they're clearly creating, the electrons are clearly creating these forces of acceleration and deceleration perpendicular a magnetic field. They're becoming magnets, and their state of whether they are excreting, what force they're excreting, north or south polar force, will change depending on what process they're in, the process of decelerating or accelerating.
in quantum mechanics, this is enough. Let's see what happens when we do some arbitrary combination. Here, since the square of this number is bigger, it has a bigger chance of being spin down, but it can still be spin up. It doesn't go 3/4 of the way down ever though, it's only ever up or down. But what about if I flip the machine on its side to measure the left-rightness? In quantum mechanics, if you tell me the wave...
So they're only using these different numbers of spin by calling those are different particles that would have a different tendency to go one way or another way, in terms of being more or less of a monopole. So now you're starting to talk about what dipoles do, not monopoles. So these different numbers they give aren't representative of electrons anymore. So she's really not talking about electrons, because electrons are always technically half spin, which means they go equal directions in both directions, equally in both directions.
Function in terms of up and down, I should be able to figure out what the wave function is in terms of left and right. To be able to do that, we just need to know how to convert up and down to left and right. But how? The coefficients should be equal in size if we use this classical analogy. A particle that's fully up can't be pointing either left or right at all. A quantum particle that's up...
So again, these are all assumptions based on their initial assumption that somehow the initial condition is not erased by the imposition of the new force. So it really doesn't matter. If it had a left and right, it's wiped out. If it had an up or down, it's wiped out. So your device is going to dictate left, right, or up, down, and there's never going to be anything in between.
But is being measured for left or rightness must go one way or the other, but at least it shouldn't be biased towards one side. Now we need to decide the sign of each of these. If we agree to call this right and that left, then it turns out that the right way to do it is this. And this is something you'll recognize from the last two videos. Okay, so now I've shown you how quantum mechanics deals with spin. Let's return to the much more...
Well, let's just understand the left and right is really just going to be a reflection of which facet of a dimension, left or right, up, down, forward, back. They're just facets of a dimension. And so it just depends on which way the force went the first time will dictate where it goes the second time and third time and fourth time.
Difficult question. What is spin? The electrons aren't doing little loops, so why are they magnetic? This was what was originally proposed. The electrons are spinning on their own axis. The idea is, if you have a charged ball that's spinning, that means bits of charge are moving in a circle, and so it creates a magnetic field like a bar magnet.
Right, so this is a huge assumption that somehow the properties of the electron are now a whole nother level of physics lower, where we're going to say the electron are little bits that are really the things creating charge. So it's not the electron that's charged, it's the little bits inside of it that are charged. So, you know, so now you're just making those little bits do the same thing, which is spin without a source of momentum. So again, where again did those little bits acquire their momentum? And do you have any evidence that that spin can be created without any, that it's inexhaustible, that once it starts spinning, it spins forever and ever and ever, that it has perpetual spin motion? When the evidence is electrons don't have any of that. They don't do velocity. They just do acceleration. I mean, it's like a real important statement I should reiterate over and over and over again. Electrons don't do velocity. They just do acceleration. Elemental particles don't do velocity. They just do acceleration. And that would be true for spin or any notion of any kind of movement. The movement has to be the byproduct of a continuous force.
But we know this is wrong. If this was really true, we can calculate how large the electron should be. It's bigger than the whole atom. It also makes some other incorrect conclusions. These days we think the electron isn't a...
So, I mean, that's sort of, you know, kind of a throwaway line in the sense that this depends on how fast you make the spin, so how big it would have to be. So I think that's stretching things to say it can't spin any faster than.
It's an infinitely small point, and that can't spin. I think this image of...
Yes, I think the image of an electron as an infinitely small point would be idiotic, because we know that photons hit the infinitely small point. You know, not unreliably. And in some substances, they hit it really easy and reflect right off, and you see it right away. So clearly, electrons can't be infinitesimally small, or you'd have to explain how the photon gets to the electron. And there's no notion that photons are charged, so how do photons bend to electrons?
An electron spinning is really more harmful than helpful. Not just because it makes all kinds of incorrect predictions, but because feeling like we understand something stops us from asking what it is. But making this video, I realized that there are lots of...
I mean, that statement is just precious. You know, you know, coming from a physics that is so confident in so many of the statements it makes about its physics. You haven't really proven that light photons are actually bent by gravity, because the math doesn't work. Your understanding of how galaxies works, that math failed, and you create dark matter and insist everybody has to believe in it. You need a lot of energy to make gravity waves reach Earth, so you create a whole new physics where you convert matter into bent space, something Einstein never proposed. I mean, your whole physics is full of assumptions that you've written as laws, and that you beat people over the head with it if they dare to say that's hasn't been proven. It's all based on a bunch of weakly demonstrated but aggressively asserted assumptions.
Other physics terms that I don't understand. What is energy? What's charge? It seems...
I have the answer to those questions. Energy is just a consequence of movement. So that's sort of what energy is. Charge is imbalances created or changes in segregation or the filtering. Charge is filtering of force. Segregating black from red creates the idea of charge, polarization. Charge is essentially polarizing the force, separating the force.
Like we define these things by how we measure them, and then the same is true for spin. spin.
You're right, and you do a very bad job of measuring them, and you have a ton of assumptions going into every measurement that somehow your device isn't changing anything. Just like the two-slit experiment. Focus on what's going into the experiment and don't focus at all on how the experiment's going to change the thing going in. How does the matter that makes up the surfaces of the two slits affect the field that the photon will travel through, or the electron, or the buckyball? And there's a huge consistency in the evidence in the sense that the buckyballs are affected the least. The quantum mechanical effect is the most dull and diluted by noise. It's less noisy with electrons, but still noisier. And it's the clearest and the brightest with photons, indicating that the object that is most directly interacting with electrons is a photon. The electrons are interacting with electrons, which create the electron pattern, and the atoms interfering with electrons are now the least deflected, because the atoms are so much more massive than the electrons they're interacting with. So clearly the field, which I would say is made of electrons around the surfaces of matter, is what's affecting whatever you throw through the slit.
Is the thing that makes particles act a bit like magnets. I really hope that in the future, as we understand more physics, more of these terms...
So energy, the ability to do work, which really doesn't mean anything. Work is just moving. So again, energy equals movement, not work. Movement is work. Okay, you can't move something for free. Matter bits. Obviously the force moves for free forever and ever. But the catch is you have to have a mechanism that imbalances it for you ahead of time to gain movement in one direction. Going back and forth doesn't do you any good. To do work, you need to go in one direction, then the other direction, or never in the other direction, in most cases, unless you're doing work at where high frequencies of going back and forth could do you some good. Because that's just basically heat. And charge, the thing that causes this force. So yes, they're filters. So here, it's a kind of interesting, because the magnets, red and blue, and then the proton, electron, I still am amazed that no one else has kind of made this connection, that it's kind of clear that protons and electrons are the magnetic monopoles.
Terms can be understood in terms of deeper physics. At least there's some hope for spin. I told you that spin had to be added into quantum mechanics.
Just kind of an interesting term, deeper physics, when really it doesn't have to be, it's nothing like deeper. It's just that it's being structured to a different set of rules. So where quantum mechanics basically, and the Bohr idea of atomic theory, was to allow for randomness and bizarreness and strangeness and all kinds of photons can do all kinds of magical things, and invisible forces and non-existent virtual forces and bent space, bent nothing things, mechanisms that consume nothing. So that was the defect here. It's not that you have to go deeper, it's that you have to go more rational. You have to stay on a plane where you're saying, well, what's the real hard evidence? What we have hard evidence of, and where do we have an abundance of evidence when we look at the big universe of entanglement? Do we see galaxies entangled? No, we really don't. Planets entangled? No, we don't really. Suns entangled? No, we don't really see any of that mush. And, the point would be is to say, if you're going to have the UFO theory, that the extraterrestrials really do exist, the woo is real, then maybe you should have the extraordinary evidence, and you have less than ordinary evidence. That would be a key point to raise here. You're making claims that are kind of wooey, kind of religious almost, or God-like claims, dark matter, extraordinary claims, and you don't even have ordinary evidence. So it's not even like you met the burden of having really good evidence, extraordinarily good evidence. You don't even have ordinary evidence. And that's a huge mistake that scientists should really understand, that they shouldn't jump the evidence. So that's another term. I'll coin it. I probably should buy the domain name, jump the evidence, because that's what science has done. It's jumped the evidence. Way ahead of it.
Mechanics in an ad hoc way. This is true, but when Dirac tried to merge standard quantum mechanics and relativity, So
yes, let's understand that Dirac always uses this miracle word, the Dirac equations, the Dirac blah blah. Dirac invented antimatter. I mean, come on. Antiparticles. He invented lots of wacky crap.
His new equation acted a lot like spin. While this was awesome, I don't feel like it solves the mystery of spin, because while it comes out in the maths, it still doesn't explain what it is or why relativity demands it exists. But maybe there are some properties of physics.
Right, so that's the whole point, is it doesn't explain what it is, so there's no recognition of any causal chain. So just like with gravity, Einstein's gravity, no source of energy. So somehow you're moving huge massive bodies, but you don't need any energy to do it, no force. And then you have magnetism, which clearly is creating an effect. That is, it's emanating of it's producing like a light bulb. Force is leaving it somehow, carrying messages. So the Morse code is going through the wire, the beep 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 beep, and yet there's no electricity in the wire. They don't account for where is the medium that's being used to convey this idea that there's more proton force than electron force. This way more proton force, this way more electron force. Somehow that's being communicated, but you don't have any carrier for the force. You just say it's just something virtual. It's an idea of a force. So you have bent space, which is a nothing, no force involved, no energy involved. And you have magnetism, which clearly is radiating something, and that radiation is altered by the magnet, therefore segregating it, making it more effective as a force. It's able to produce energetic results. Yeah, so there's just no, so that should be the giveaway. Just as like when you talk about an electron, you should always recognize it can be accelerated, but it can't hold velocity.
That we can never understand, and maybe spin is one of them.
So again, put it in this, we don't have a very good answer, we don't have very good evidence, we're just speculating. Therefore, because we haven't figured it out, there must not be an answer, because we're really smart and we didn't get the right answer, so there must not be a right answer. No, the argument would be is that 300 years ago, somebody proposed an idea about a mechanical gravity system, and they all scoffed at it because they found one flaw, and they just said, forget about it, we don't pay any attention to that. Yes, it explains 90% of gravity, no, 99% of gravity, and has this tiny defect where, yes, it looks like there should be drag and there isn't drag. And so instead of trying to explain why there's no drag, why material objects can travel through space without drag, instead of trying to explain why that takes place, and in the context of admitting that you have no theory of inertia anyway, that your conventional physics has no clue why how this pen is different when it's moving, and how this pen is different when it's standing still. You don't have any knowledge or explanation for why, when the pen's moving, it keeps moving in space, and what exactly has changed with the pen that's not moving. You don't have a theory. And so in complete ignorance, you dismissed a mechanical model, and then in the end you all ridiculed Einstein for saying, no, there probably is a mechanical model, we just haven't found it. And instead you all voted for your wooey theory with your magic dust and your unicorn dust and all this fairy princess wands and shit of all this magical forces and magical events and the tiniest thing in the universe, or battleships with radar, and they can do all kinds of fancy things. They can split in two and fly in different places, and they can entangle with each other, and they can do all kinds of fancy shit. And they're supposed to be the simplest elemental particles in the universe. I mean, this doesn't have anything to do with the fact that finding the truth is hard. This has to do with it's impossible if you have a woo bias. And what physics has had for over 100 years is an incredible woo bias, a religious bias. They can't even describe their own history correctly. Again, Newton discovered the interference pattern 300 years ago in the single slit. And you people just keep talking about how Young discovered it. He didn't discover anything. The envelope idea wasn't even in Young's discovery. The idea that the two-slit pattern fits inside of the single-slit pattern wasn't part of Young's discovery. I mean, it's just, you know, so you rewrite the history. I mean, this is about doing bad science. This isn't about, oh, the truth was so hard to find. No. You're not going to find it at all when you're not really looking for the truth. And science hasn't looked for the truth.
There was so much more I could have said about spin, but I ran way over time. So I thought it would be fun if you guys taught each other instead. In the description, I put a whole lot of questions I didn't answer in this video.
17 of them, yes, actually. And sort of, you know, not, you know, well, anyway, fine, yes, good idea.
I would love if you picked one or more of these or found your own and did some research.
Yes, I'll find my own, but, and I clearly have answered a few of your questions in this video. But yes, some of them were just simple Wikipedia, kind of, you know, go look it up on Wikipedia. You know, that's not really doing anything.
You can present your work in any format you want, as a YouTube comment on any of these social media accounts, or on your own website, etc. And it would be kind of amazing if you want to make it into a video, but...
It was kind of curious that actually in one of the questions, Hofladay was credited as causing one of the questions. I should look that up, right, because that was kind of funny. But it was on isospin. I don't even remember what the hell isospin was. What is isospin? Why is it that even though it hasn't got the units of angular momentum, it still formally acts like spin, according to Wiki? Thanks, Hofladay. So, Hofladay got the 17th question. Yeah, these viewer-added questions I don't think much of. What happens to the electron if you put them in the Stern-Gerlach machine and then slowly rotate them up and down to side and side? Do some of the electrons switch places? Now, from their orientation, they're not paying much attention to gravity or any other previous orientation, so they just keep doing what they were doing, which is if they were doing this up and right, up and down thing, now they're just going left. So they were essentially going all the way up or all the way down. Now they'll just go all the way right or all the way left. So no matter what position you rotate them in, they're going to be going all the way in that rotation. You won't change the results any. Alright, yeah, so I'll finish this.
I know that's a bit daunting. As for the content, you should know that some of the questions I asked in the description are ones that I don't know the answer to, despite trying to find out. So it's absolutely fine to just make an attempt. This doesn't have to be a huge thing.
Yeah, but I mean, physics really should be. It should be a huge thing that, you know, all this stuff is talked about in the accurate context, in the sense that, you know, these little cheats, you know, like in this video, you know, assumptions made about what the two-slit experiment does or the single-slit experiment does. Assumptions about the fact that an electron is a little magnet when there's no theory defining it as a little magnet. It doesn't have two poles, and it isn't a little magnet. It is one of the carriers. It's one of the force carriers of magnetism, the force filters of magnetism. It's one of those players, clearly connecting it to magnetism, but it isn't a magnet.
Also, a lot of sources claim to answer these questions, but leave big gaps or make potentially unjustified assumptions. And some of these questions...
Yes, like every video on the internet. Like every physics video about quantum mechanics has huge gaps in the evidence provided, the proof for the assertions, and all of the axioms stated as known fact. None of them are deserving of their status as proven axioms.
Are still unanswered, even though there are some interesting leads. So then, your task isn't necessarily to definitively answer your question. In fact, I'd way rather you point out why you don't understand something, or discuss several possible solutions. Don't worry.
You really can't do that, so that's part of the problem, is you can't take the wrong answer, okay, and keep its wrong character and just fiddle with it and fix it, unless you get to the core of the misunderstanding. So again, it's this whole wave-particle duality. There is none. It's either a particle or a wave. It's either a material universe or an immaterial universe. You can't fudge those. And so trying to rework something built on a bad axiom isn't going to help you much. It's not going to get you to the right answer. So you're better off not fiddling with it, but reconstructing it. Because that's what I did, and it was really easy. Yeah, it's really easy to fix it if you just start over.
About being dumb. Not knowing things isn't dumb, but pretending you do is. I'd love if you read each other.
So, I mean, that's a nice little cliche, but again, it's like what people know, what even physicists know, is sort of sometimes is a very easily demonstrated point. You could argue where they don't understand the history correctly. I could point out how the talking heads of physics, every single one of them can't describe the double slit experiment accurately and what it represents, what the difference is between the two slit and the single slit. They won't even get any of those answers right. Yet that foundational experiment for the entire subject of quantum mechanics, I mean, it really is the subject. It really is the source of the entire field of science, and they can't get their foundational experiment. They don't even have knowledge of it. That's how full of assumptions they are rather than knowledge.
Others' responses. If you want to give any constructive feedback and start a discussion, then awesome. I encourage...
what is that, a bow tie? Or very high boobs? Yeah, I'm not sure.
Encourage that so much. But just remember to be kind. Anyway, good luck, and
disagreeing is good. No, really, disagreeing is a pain in the ass. So, you know, it sucks, but, yeah, we have to do it. Being mean isn't. Right. I agree that being mean isn't good, but disagreeing isn't good either. So this whole idea that there's good in here somewhere is probably a mistake.
I'm really looking forward to learning things from you.
Yeah, I don't know. That sounds a little bit like you're kidding me. You know, that's like one of those flirty girls or something. Yeah, I don't think you're all that excited. But anyway, yeah. I think this was a worthwhile video. Lots of stuff in it. It's a little complicated when you get into little details and stuff, and you really have to get the idea. It's a visual thing, you know. There's no bent space. There's no magic forces. Everything has to, the matter bits have to be pushed by the force bits, and the matter bits always lose whatever you give them. So if I push an electron, the electron very quickly will lose that momentum. The field will take it back. It will recreate a balance and absorb the imbalance in that location. And so it's really important to understand those little bits of information. Understand them conceptually. Understand that the force has all the speed. All the force bits are moving the speed of light, and the matter bits are basically just being moved around by the force bits. That's the way to see it. The energy is all force, and the matter bits don't have much to do with doing anything until they're in an arrangement where they're capturing force, like the space shuttle captures the force. The big flame of the opposite reaction goes inside the space shuttle. So the big flame going this way, coming out of the tail. There's another big flame going right into the space shuttle called energy. And it's absorbing it. It's collecting it. And that's why it keeps moving. It's because it owns it. It possesses it. And it's not giving it back until it hits a brick wall or blows up or some other thing. So anyway, till the next time, and such and so forth and whatnot. Horribly long video, but, you know, it's a horribly big subject in a way. It's a big conversion. You're taking something that's this way and you're going to flip it all the way over this way. So you have to do this whole flipping thing. You know, you just can't move from here to here. You know, you have to flip it over. So it takes more work to do that. So anyway, till next time.